my molecule of interest. So when one electron is removed, then what happens is that my molecule gains a positive charge. So it is basically M ion, M plus 1, that is ion, not a, it is, there is no change in the molecular weight, but there is a plus 1 charge which it gets. So that is basically, then when I call M by Z, when I say mass to charge ratio, my molecular weight is the M and Z is the charge, that is 1. So that is the ion which represents basically the molecular weight of that particular unknown species. So that is typically called as a molecular ion, which is a very critical for me. I want to know molecular ion definitely, because without knowing the molecular ion, in the mass spec as we see that we can see only the either fragments we can see, or we can see the molecular ion. So without the molecular ion, only with the help of fragments, I won't be able to do anything. I won't be able to really elucidate the structure. So that is why we will always need both. That is, fragments also we need and molecular ion also we need. So we discussed about the requirements of various ionization technique. Why? Because different molecules will have different properties, and naturally some of the molecules may give me the molecular ion and fragments by using some ionization tools. We took an example of a chalk and duster. If I put a large force on chalk, then chalk will completely get powdered. And whereas the same force if I put on a duster, which is a wooden duster, it may just get fragmented into 2-3 big pieces. So some of the molecules are very stubborn. Although I am putting lot of energy, that is, I am bombarding with a very high amount of energy, they may not get fragmented too much, and they may show me the original species, right? Basically the molecular ion it will be seen. I may be able to see the fragments also. Whereas in case of a chalk, as I give an example, if it becomes powder, that means no traces of the original species, that is chalk piece, is seen. Only a fine powder will be seen. So that means only the fragments will be seen, a small fragments, which I may not be able to see or elucidate the structure, because I will always need fragments also, and I will need the molecular ion also. So based on various requirements, we basically studied last time. One was the EI, which is basically high energy electrons, which is 70 electron volts is the energy which bombards. Why EI and why 70 electron volts? That we studied. 70 electron volts is an optimized energy. Scientists studied from the lower to the higher, and they found that maximum amount of information is generated when electrons have the energy of 70 electron volts. If it is lower, then there is a less fragmentation. If it is a more energy, then there is very large fragmentation. And when there is a very large fragmentation, then I won't be able to do interpretation part. So that is why EI, in case of EI, 70 electron volts is fixed up, which is worldwide. The next one we saw was CI. Now when EI also, that 70 electron volts becomes higher energy for some of the molecules, I may be able to see only fragments, but I may not be able to see the molecular ion. If molecular ion is not seen, I will always need the molecular ion and fragments in a mass spectrum interpretation. If molecular ion is not seen, very difficult to interpret that mass spectrum and to elucidate the structure. So those cases where we saw some of the, particularly I told you, long chain aliphatics like decane or maybe higher sub or maybe many other compounds, those materials when bombarded with a high energy electrons, they will get fragmented to very small fragments. Nothing but no molecular ion traces will be seen. So that is why there I am going to use an alternate technique, which is basically, I will say, an add-on to the electron ionization, that is chemical ionization technique. So in the chemical ionization technique we saw, you need EI anyway, EI data, and in the CI you introduce a reagent gas. We saw the 3 reagent gases, that is, one was methane, isobutane and ammonia. And when there are 3 reagent gases, we saw ammonia is a very good gas, but because of the corrosion and other properties, it is less preferred in the industry, whereas methane is available in a very pure form and is the most preferred reagent gas in chemical ionization. For interpretation of chemical ionization spectra, you will always need electron ionization spectra, plus you will need the chemical ionization spectra. Chemical ionization spectra will give me M plus 1, that is, it will give me an indication about the molecular ion or possible molecular weight, and EI, electron ionization, will give me indication about the basically what kind of fragments are there. So when I couple the information, combine the information of the molecular ion or the possible molecular weight of the molecule and fragments, then I will be able to see the structure. I will be able to interpret the structure of that particular molecule. This is what we saw. Then one more topic we saw was negative ion chemical ionization. So whereby those species which are electronegative in nature, instead of one electron getting dislodged, it is possible they may capture the electron, because whether electron gets dislodged or not, or electron gets captured or not, it all completely depends upon the electronegativity of that particular molecule. If the molecule is too electronegative, it will always love the electrons, and instead of electron getting dislodged, it will capture the electron and may become negative ion. So that negative ion, which is again because of it's a chemical ionization process again. So that is very sensitive mode, because we discussed again something called S by N ratio. Everybody must be remembering that. So as your signals may be low, but if the noise also further reduced, then you will have the better sensitivity for the estimations. So that is what we saw. So now, so those techniques EI and CI typically use EI particularly for volatile species. So EI is a very popular technique for GCMS. Now what about those compounds which cannot be analyzed on GC? Because as we discussed, the prerequisite of a GC is you need to evaporate the compound. If you are not able to evaporate the compound, then you won't be able to analyze that material on GC. And naturally EI also needs a material which is evaporated. So EI, GCMS is not possible for those compounds. So the technique which is typically used, again GC is an inlet system as we discussed. It is one of the part of mass spectrometer. Mass spectrometer is coupled with basically an inlet system. So whereby it is sample is introduced through that inlet system into the mass spectrometer, and the next series of compounds which are not evaporable but they can be dissolved. We discuss if I can dissolve, I can resolve on LC, that is liquid chromatography. So another typical type of technique which is the most popular today in chemical industry, in research everywhere, is LC mass or LCMS. Now the sources which are going to be there, that is ionization sources which are going to be there in, are going to be different as compared to the your GCMS sources. So EI and CI are not used with LCMS, but now let us start with the first of our historical sources, some of them, and then we will go to the which are used today. Is this clear? Any question on this? Then we will move ahead. Is it clear?
Yes, sir, it's clear.
Okay.
No, yes, sir, yes.
No or yes? Clear? Okay. So
Yes,
now
sir, yes,
let's
sir.
go ahead. I will start sharing my presentation. Can you see this?
Yes, sir.
Okay. So now let us keep these slides. We already seen last time. We will now go to the LCMS. Is now the first one which was introduced for LCMS ionization source was thermospray. With the thermospray setup, LCMS became the routine analytical tool in large number of laboratories. It was the first source. If you see EI is a source which is it is there, but it is like a standalone. But it is not an interface. Interface is separate. Whereas in case of a thermospray, it was the first interface. Interface means which is connecting the chromatography system to the mass spectrometer. That is called interface. Interfacing the two techniques. Okay, so that is interface. In GCMS, the interface typically used is a transfer line. You don't have a separate any special interface there. There is a transfer heated. So if somebody has seen the GCMS, you will know that your column is heated, your transfer line also is heated. So transfer line basically the evaporated molecules which are coming out from the GC portion, that is from the column, they are carried forward to the mass spectrometer. They go to the ionization source and then followed by the mass analyzer. So here in thermospray, the transfer first interface in which ionization also is done directly from a solution. So you do not need a separate interface like a transfer line in GCMS. You don't need this. So this is the ionization source, which is an interface also and which generates the ions also. So this was the first interface in which ionization is effected directly from the solution within the interface itself. That is, the mass spectrometer was not used to produce the ions. So this interface takes care of the two, basically the responsibilities it has. One is to interface the LC part to the mass spectrometer, and second is that to generate the ions. So those ions which are generated, then subsequently they are thrown to the mass analyzer portion and mass analysis is carried out. So this mass spectrometer was not used to produce the ions, and mass analyzer was simply used to have the separation of them according to the M/Z ratio. So thermospray as such, you can see that all these are called spray techniques. There is a thermal and spray. So most of the techniques which are used in LCMS are spray techniques. Now, before going into the details of the thermospray, there has been always lot of issue of interfacing the LC part to the mass spectrometer. Why there was a lot of problem? Because the volume, see what you need is that although liquid chromatography has the liquid as an eluate, but the mass spectrometer cannot analyze liquids. Why mass spectrometer cannot? Because it needs everything to be evaporated, because it needs in the ionic form, and those ions subsequently they travel to the mass analyzer portion. So you need to put them in the gaseous form only. So the first thing what you need from an LC is to evaporate that solution to the gaseous form. So now you can imagine when a liquid is evaporated to the gas, and when there is already gas, will there be a change in the volume? Will there a change in the volume?
Sir, can you repeat one more time?
See, I have got, let us suppose 1 ml of a gas. Okay, let us take a simple example of water. Okay, I have got 1 ml of water vapor. What is the molecular formula of water?
H2.
H2O. What is the
H2O.
molecular weight of water? What is the molecular weight?
18.
H2O. So what is the molecular weight?
18.
18. So 18 is the right molecular weight of a water. Now, if let us suppose I have got 1 ml of water vapor. Now I am just comparing GC portion with an LC portion. Okay. Now when the GC is there, when I am introducing a gas, I am introducing a gas, or that gas is going through the mass spectrometer. It is 1 ml means 1 ml. There is no further increase in the gas volume. Whereas in case of an HPLC, another one difference is that I am injecting a very small quantity of liquid also, 1 microliter or even less than that. I go to the split modes and other things. I am not going to the details of those things because I presume that you are fully aware of what are the other injection techniques in GC. So like a split mode, there is a splitless mode, there is a burst pack mode, there is on column GC, like that there are various modes of a inlet system for GC, which is an injection portion. So that I presume you are fully aware. So in GC, when 1 ml of gas is there, 1 ml gas, there is no further treatment to that is gas. So 1 ml remains as a 1 ml. That everybody agrees?
Yes, sir.
Yes, sir. Yes.
Yes,
Now,
sir.
in case of HPLC, apart from your sample, your liquid is flowing. Okay. through the LC portion. Right from your, what is the first step in LC? That is, you have got a solvent reservoir, right? Solvent reservoir is there, then there is a pump system is there, right? Then there is a injection valve is there. So this injection valve, basically you are going to have the injection of a sample, then subsequently that injected amount is carried forward by your solvent which is flowing to the column portion. Then column separates your components of interest, and then the column throws all those things one by one, all those components to the detector portion. The detector detects, generates the signal, and those signals are recorded by the computer based system. That's overall portion of a LC, liquid chromatography. Now that is why, irrespective of any sample is there, you will always have liquid flowing to that from the solvent reservoir to the outlet of the detector. Now here you can imagine I am interfacing LC portion with my mass spectrometer. Now I told you this thermospray, which is not only an interface but it also generates the ions. Now when typically in LC, when I am having GC, I have got a flow rate of something like say 40 ml per minute, that is a gas. In case of a LC when I am using, then I am having a flow rate of 1 ml per minute. Generally the HPLC flow rates are around 1 ml per minute, right? Everybody agrees with this or no?
Yes, sir.
Yes, sir.
They may be different little bit. Some of the LCs, they will have very low flow rates. Can anybody name which are the LCs whereby you have got a very low flow rates? You must have learned a lot in last year about HPLC and various techniques in HPLC. Anybody tell me whereby you have got a flow rates very small in LC? A special technique is are there which are most popular today.
Microflow LC.
It's basically UPLC. It is called
Okay,
UPLC,
sir.
ultra high performance liquid chromatography. In UPLC, the flow rates are to the tune of 25 microliter, 50 microliter, that kind of flow rates. So 25 microliter is very small. You have got a normal LC, you have got a 1 ml, means 1000 microliter. Instead of 1000 microliters, you have got 25 microliter. So very small flow rates. Now coming back to our topic. So when 1 ml of liquid is flowing continuously, now let us take a test case of water is flowing through my LC. And this water is continuously going to the thermospray portion, that is my interface. Now this final interface has to get connected to my mass analyzer. Now when 1 ml of water gets evaporated, how much gas it will generate? Can anybody tell? You must have learned classical thermodynamics in 12th standard. This is all 12th standard. This was not, I am not talking about BSc or MSc level. This is all 12th standard. See, there is a general law, that is gas law. When 1 mole of liquid evaporates at normal temperature and pressure, then 22.4 liters of gas is generated. Anybody remembers this? Anybody remembers?
No,
Yes or no?
No, sir. No.
No? Okay. So now you must remember that when 1 mole of a substance is evaporated, it will generate 22.4 liters of a gas at normal temperature and pressure. Okay. Now you can imagine if I have got a flow rate, okay, I have got a flow rate of 1 ml, and there is a, generally your HPLC columns, your injections, when they are injected, one run maybe 15-20 minutes easily, right? It will take minimum
yes,
20 minutes for generation of your chromatogram. So if I have got a 20 ml, or 20 ml is equivalent to 20 grams, 20 ml is equivalent to 20 grams. Now 20 grams of water is I am pumping, then it will generate 22.4 liters of gas straight, because 18 is the molecular weight of water. So 18 grams is going to generate 22.4 liters. That everybody agrees or no now? Because I have told you already, 1 mole of a substance you will generate 22.4 liters of a gas at NTP. Okay. Now water, the molecular weight, somebody has already told me that it is 18. So it is almost, if 18 ml of liquid or water is evaporated out, then 18 ml or 18 ml, I am saying 18 grams. Why? Because the water density is 1. Everybody must be, right? So if 18 grams are evaporated, it will generate 22.4 liters of a gas, which is a very huge quantity. So the combining, so the why this whole amount of gas is a problem? Because my mass analyzer portion has to be under high vacuum. We learned that. Otherwise, I have got a problem of mean free path, and I will not get ions, reproducible ionization patterns, because ions will be lost. So I need something whereby my interface has to work out so much that it should not overload large quantity of my liquid or the gas onto the mass spectrometer. That is another requirement. So that is why it was a very difficult propositions for interfacing the liquid chromatography to the mass spectrometer. So this was the thermospray, as I am saying, is what I said is clear just now. 1 ml of a liquid and 1 ml of a gas, what is the difference? Because the gas liquid
Yes, sir.
generates a large quantity of water vapor, and 1 mole generates how much water vapor? 1 mole of a water, how much volume it generates?
22.4.
22.4 liters. That's a huge. So if that is so, my mass spectrometer, if I am putting, let us suppose in 20 minutes run, I am putting 22.4 liters of a gas on my mass spectrometer. My vacuum will completely go off, because it will not be able to take out this much gas outside the, means pumping system will not work at all. Pumping system will completely fail. So that is why the interface has to be such in such a way that it is able to take care of this kind of load of a liquid also. So that is why it was a very difficult thing. So that is why UPC was developed back, whereas LCMS took little time, because the interfacing the liquid chromatography with a mass spectrometer was the most difficult thing, because it has to take care of the load of liquid. See, that is why I told you, as compared to the conventional LC, the today UPLCs are preferred for LCMS, because the flow rates are very very small. I told you just now, instead of 1000 ml, 1000 microliter flowing per minute, it is 25 microliters. So very very small. So that is why today's LCMS, good LCMS, are all UPLC coupled with a mass spectrometer. So that is LCMS only, but it's a different form of a LC. It's a UPLC coupled with a mass spectrometer. Now let us go further ahead about the thermospray. So now let us see thermospray, how it works. So again, I told you this all techniques everywhere. You need to evaporate the ions have to be in the gaseous form. They can't be in the liquid form. So when I am coupling my liquid chromatograph to the mass spectrometer and I am having a thermospray as an interface, thermospray works both ways. That is, it basically interfaces the liquid chromatograph with the mass spectrometer as well as it generates the ions. So what we'll do, we'll just see this theory, these 4 steps, and then we'll take a break for 5 minutes. So basically in thermospray, the ionization comprises of the 4 stages. The first stage is the formation of the droplets from the HPLC eluate. Anybody remembers have you learned atomic absorption spectroscopy? Have you learned atomic absorption? AAS?
Yes, sir.
Yes.
AAS needs the first step in AS. What do you need? Can anybody tell? What is the first step in AS?
Atomization of sample.
Nebulization. Absolutely. The nebulization and atomization of the liquid what you are pumping. Why it is required? Because you want that it has to be completely in the fine droplet form, because you are going to use absorption spectroscopy. You can't just use liquid there. So that is why those materials, they should be in their free state, and then they can absorb their characteristic radiations or the characteristic light. Similarly here, see now there is no light here, so do not confuse about that. But formation of a fine droplets is very very required from the HPLC eluate. So after the formation of the droplets only, fine droplets or the nebulization, then only the further subsequent steps they will work. So the second step is charging of these droplets. So these droplets are charged. Then third step is desolvation. The droplet which is comprising of your solute of interest and a solute and your solvent. Because when you are doing LC, your solute is dissolved in the solvent. But solvent is only a carrier. Are you interested in the solvent? You are not interested in solvent. Solvent has to just do its work of carrying your solute through the liquid chromatography. Subsequent to that, the solvent has to get out. So that is why desolvation or the removal of the solvent portion from the droplets, whereby only the solute ions are there. Then formation of the ions from the analyte. So these are the 4 steps. We will see in more detail. Now we will take a break for 5 minutes. Okay?
Okay, sir.
Okay, sir.
Yes, sir.
Shall we continue?
Yes, sir. Yes, sir.
Okay. So as we are discussing, the ionization comprises the following four stages. You can see the presentation.
No, sir.
You can't see presentation.
No,
No,
sir.
sir. Presentation.
Correct?
Presentation is not visible.
No, but till the break, your presentation is visible or no?
Sir.
Yes, sir. Yes.
What happened then? Just a minute. Now is it
Yes, sir.
visible?
Now it's visible. Yes, sir.
Yeah. Yes, sir. Yes.
So ionization comprises the following forces as I discussed. So just like as you saw in AS, there is a formation of droplets from the HPLC eluate. Then charging of these droplets. So the droplets are charged. Then desolvation of the droplets because you do not want a solvent. Which are the typical solvents used in HPLC?
So methanol.
And methanol is one. What is second? Very typical. Minimum 3-4 solvent you must tell. One is methanol. Second, water. Is it not used very ample?
Yes, sir.
Yes, sir. Yes.
Then third,
Distilled water.
what is the third? Acetonitrile. Anybody remembers or no?
Yes, sir. Acetonitrile. Yes.
Acetonitrile is typically used a lot. So these are the three solvents which are the most popular. In addition to that, you can use many other things like there will be buffers. There are buffers which are used typically in HPLC. Why buffers are required? Because again, I do not want to discuss a lot on HPLC because you know all the HPLC very well. Buffers are used basically in order to have the proper separations and the shapes of the peaks. Because in without the buffers, you will find in the some of the materials which are acidic or basic, they will not show a proper shape and separations also. That is why buffers are used. Which are the typical buffers used? Anybody tell? Can anybody tell? Just name few buffers. Salts. Basically, you have to name salt.
Phosphate,
Huh?
phosphoric acid.
Phosphoric acid is used, but basically phosphoric acid like orthophosphates, you will use in
Yes,
the form of phosphates. Okay, you will use acetates typically. Okay, ammonium acetate, sodium acetate, that kind of buffers you will be using. And so dihydrogen orthophosphate, potassium dihydrogen orthophosphate, sodium dihydrogen orthophosphates, these are typically used. So they are basically the purpose of the buffers. Now one of the important thing you must remember with the buffers is that the buffers have to be preferably evaporable in nature. So that is why the organic based are typically used because you can use sodium acetate also, you can use ammonium acetate also. So that is why ammonium acetate is a preferred buffer or the salts as compared to sodium acetate. So all those things will come to more and more in. You can hear because I am just getting some message that
Yes,
all quality is poor. Can you hear properly?
yes, sir.
Yes, sir. We can. I can hear, sir.
Okay, okay. So now let us see how is this. So as I said, buffers are used. So desolvation of the droplets because these, as I said, you were named just now solvents which are there. Acetonitrile, water, methanol. These solvents have no role in the case of mass analyzer or the ionization. Okay, these solvents have to get out. Some of these solvents have a role in the different ionization but not in thermospraying. So desolvation of the droplets is very very essential and then the formation of the ions from the analyte. So the solute ions you are interested. You are not interested in the ions of the solvents. Okay. So this is typically how the thermospray looks like. So various parts of thermospray are there. You can see right from the A to L. Let us see one by one. The A is a direct heated vaporizer. Okay, so which is going to basically heat the portion of the material which is coming out from the your LC portion. So this is an interface. So this interface is always in between LC and mass. So this A is a direct heated vaporizer. Then B is a vaporizer thermocouple. What is thermocouple? What thermocouple does? Anybody knows what is thermocouple? Silent. Why
It is
silent?
a it is a sensor that is used for measuring the temperature.
Absolutely right. So it is basically thermocouple is used for temperature measurement. So I want thermocouple here to know the temperature also, because I can tune my heating source based on that. If my temperature drops too much, then I will heat the material. If my temperature is too high, then I will reduce the heating, because I want to maintain a constant temperature. Okay, so that is the thermocouple job, to give the signal. Thermocouple will only give me the signal about what is the temperature. Then next comes the filament. Now filament is basically used for the charging of the molecules. Then D is the discharge electrode. Then E is the ion exit cone. So this is the ion exit cone. Now you can imagine A and B, you are seeing this is the portion from which my liquid from the liquid chromatograph is coming out. Okay. Now this is from here, it is heated up. Okay. It is heated, there is a filament also for charging my species. Then subsequently this comes out as a fine droplets are coming, basically the nebulized one, and from here there is a discharge electrode also here. Here then the ions are formed because of the filament and because of the heated this thing. Ions will be, so it's a thermal ionization, thermospray. So ions are formed in this particular portion. Once ions are formed, subsequently to this, there E is the ion exit cone. So these ions are formed. You can see this. What I want in the upper portion where you are able to H, G, all these things. This portion is the mass spectrometer portion. Okay. This portion I is basically pumping portion. This is going to the pumping section. So the spray which is coming from this here, which is going to the mass spectrometer, it is first getting nebulized. First it is getting nebulized, as you saw. The first is the formation of droplets. Then there is a charging of droplets because of the filament. Okay, the charging of the droplets because of the filament. Then when it is already, it is heated, there is already heat already there, because there is a direct heat vaporizer is there. Then there is a charging of that particular droplet also. Simultaneously, then there is a desolvation of the droplet, that is solvent molecules, they are going out from the droplets whatever are formed, and only solute ions are left. And when that is so, after the desolvation, the formation of the anyl ions from the analyte. So here in this portion, which is my cursor is there, can you see the cursor?
Yes, sir.
Okay.
Yes, sir.
Yes,
So this
sir.
cursor portion here, this is my material is coming from a liquid chromatograph. First it is getting heated up. Then, so there is a formation of the droplets is there. Then there is a filament is there, which is charging my droplets. After that, there is a desolvation. In this portion, there is a desolvation of my droplets. So desolvation means solvent molecules are removed, and only solute which is coming out from here is remaining there. So these are the charge. So once the desolvation occurs, then the charged species of my solute, they are formed here. So these species, now here you can see there is an ion exit cone. So this ion exit cone is a portion of the door which is only allowing my ions to go to the mass spectrometer portion. Now here what I am doing, this is the first, I am having lenses. These are the all GR lenses. Lenses means which will only allow the ions of the right type to pass through. Okay. Once these ions are there, now these ions will get attracted to these lenses only if it is the opposite charge. So these ions are all positive in nature. Here the first lens is negatively charged. So this is the lens or the portion which is negatively charged. because it is negatively charged, these positively charged species or the positive ions, they get attracted to here. Is this clear?
Yes, sir.
Okay.
Yes,
Yes,
sir.
sir.
The solvent molecules which are formed, or the solvent vapor which is there, which is formed because the desolvation is not a charged species. So these charged species, they will not get attracted to this ion exit cone, because these are the lenses which are, this is first lens is a negatively charged. Since the solvent are not charged, they will not get attracted here, whereas here this is the portion which is I is showing, basically it is the liquid nitrogen trap or the 4 pump or the pump, basically pumping system. Nitrogen traps are typically used. Nitrogen is a liquid nitrogen trap. It has got a temperature of minus 196. Okay, so minus 196, the liquid nitrogen. Anybody has seen the liquid nitrogen? How does it look like? It comes in gallons and it has got a temperature of minus 196. You can imagine, when there is a minus 196 temperature and a pumping system, these all solvent molecules which are there in the vapor form, they get pumped. They get, why they are getting, the pumping system is there. At the same time, they will get condensed also, because minus 196 temperature when it sees, immediately all those solvent molecules which are in the vapor form, they will form liquid and they will go to the trap system. Then there is a pumping also. All those other molecules which are not forming liquid, they will be going from this pumping system. So there is a two-stage pumping in this case. So what are the two-stage pumps? We remember, anybody remembers? We learned this in the last lecture. Which are the two pumps typically used? Two pumps.
Turbo
Yes.
molecular pump
Turbomolecular pump
and
and
oil diffusion.
rotary pump. See, oil diffusion pump and turbomolecular pump are not
Yeah.
used together.
Rotary.
Either of them, either turbomolecular pump with a rotary pump or oil diffusion pump with a rotary pump. But today I told, as I said last in the last time, that oil diffusion pump, since it also produces some of the your interfering species because of the oil, it is not used much. Whereas turbomolecular pump is the most popular. So in the today's aspects, I will say here the pumping system will have turbomolecular pump and the rotary pump. Okay, so these are the solvent molecules which are getting attracted because the pumping, they are going here, there is no charge on the solvent molecules, they go to the pump portion, they will be thrown out. So what I am doing in this case is that I will give you an example of one, let us suppose 1 ml of water vapor is there, it will generate large quantity of gas, but this gas which is generated because of water vapor is going completely out from my pumping system here itself. So this is a portion which is the ionization portion. This is not a mass analyzer portion. See, I need a high vacuum where I need, once my ions are formed here and they are extracted into my mass analyzer portion, then I do not want any other ions to come in between. So this is the portion which is a high vacuum portion, whereas this is the portion which is a low vacuum portion, because it is connected to the all vacuum system. So my ions which are formed here by 4 steps. First is that the formation of a droplets, then charging of these droplets because of the filament, then I got dissolution of the droplets, that is removal of the solvent from my droplets, and then the formation of the ions. So here liquid is coming, then followed by heating of that liquid, there is a vaporization of the liquid, then there is a filament is charging those droplets which are in the liquid form, vapor form, then there is here the dissolution of the my droplets will be there which are in the vapor form, and once the dissolution occurs, then ions are formed. These ions get attracted to my ion exit cone. This is the negatively charged lenses is there, because since my ions are positive in nature, they get attracted here. So this first lens is a negative, the second lens is a positive. Why I want positive? Because once these ions are speedily going, I want them to be collimated to form a fine beam. So that is why once there is a positive charge to second lenses, then there will be repulsion of these ions. So they will form a very very thin beam. Then again here I want to accelerate, so it will be negative. The first lens will be negative, second lens will be positive, third lens will be negative. So once this is from this portion, the ions of positively charged species, they are coming and they go to the mass analyzer. This H is shown as the mass analyzer portion. From this side, all the solid molecules are going out from the system with the help of a pump system. So some of the other things, so this H is the quadrupole assembly is there. This J is a source block heater, because this whole thing, I think I want it to be in the heated portion. That is why there is a J is a source block heater. So this is the completely this filament type you are seeing. This is not a filament. This is basically a source block heater. And K is a source thermocouple, which basically regulates the or gives the signal and tells about what is the temperature. And then L is the repeller. This portion is the repeller. So basically a positive charge. So this whatever the ions are formed which are positive in nature, they preferably go on this portion to the mass analyzer portion, not otherwise. So all the ions travel like this, all the solid molecules travel like this. So that is how this interface, which was the first interface to couple LC with MS, was very very successful to efficiently form the ions, and these ions are formed. So interface works as interfacing for LC to the MS also, as well as it generates the ions. So the ions which are free from solid molecules, they are then taken to the mass analyzer. Is this clear?
Yes.
Yes, sir.
Yes, sir.
Any questions on this? What is the purpose of
No.
the lenses? Why lenses are used? Anybody can tell? Why lenses are used? What is the purpose of lens?
They attract the molecular ions.
They attract and repel both. The first, not molecular ion, it will be attracting all the fragments. It may be a molecular ions basically. See, when the ions are formed, this portion doesn't know whether it is a molecular ion or it is a fragment. Anything, the fragment also is a positively charged species. The molecular ion also is a positively charged species. So anything is there. It is only ions, whether molecular ion or fragment, that will be known by the mass analyzer subsequently. So this is how it works. So the lenses, the job is to attract, then subsequently second lens is to repel to form a collimated thin beam, and again the next lens is to again attract to speed up the ions, which should go to the mass analyzer portion. So that is how the mass analyzer, the thermospray works, and the ions are successfully thrown to the mass analyzer portion, and these ions are free from any solvent. So this is the portion typically at a very high vacuum. Okay, this portion is kept at a high vacuum. Up in the vacuum here, whereas here the vacuum is low, here the vacuum is low, here the vacuum is low. Okay. Sorry.
Yes, sir.
Yes, sir.
So these are already seen. So let us see the advantages. Okay, what are the advantages? It is very easier at this is are all advantages which were, I will say, when the thermospray was introduced. Okay, now today thermospray is no longer used as a technique because there are better techniques available than thermospray. But in 1983, thermospray was the first technique to be used as a spray technique for the LC and MS. It is very easier to use than other available alternatives. That way, whatever there were studied at that time, this was the most easy. Can operate under a wide range of HPLC conditions. So regularly HPLC flow rates. Since it allowed to couple with normal LC with the MS, a normal LC the flow rate used to be around 1 ml per minute, and it allowed the normal LC to couple with a mass spectrometer. Okay, so whereas at that time there was no UPLC, it can allow unequivocal determination of molecular weight, as thermospray usually contains ions simply from the molecular species with little fragmentation. Generally, all the techniques which are spray techniques we are seeing, which are LCMS techniques, they will have very less fragmentation. They are called softer techniques. Which are the techniques? Last time what we studied was the harder technique, I told you. So the first one, which was the most hard technique which is introduced, was electron ionization. Whereas CI is a software technique. The thermospray, the electrospray, all these techniques are called software techniques. So generally they will have definitely the molecular ion, plus they will have some little fragmentation, not very large fragmentation. So again there will be some modification required in order to get more and more fragment, that we are going to study afterwards. Another advantage is that there is a discharge electrode we saw and a filament of the thermospray also saw. So it allowed the discharge electrode and a filament not only based on the thermal principle like only heating and formation of ion. That was the initial thing. Subsequently, when discharge electrode and filaments were introduced, they allowed the charging of the species to the greater extent. Okay, and then the formation of the species was much better as compared to the earlier thermospray without discharge electrode and filament. Okay, with discharge electrode and filament the charging was much better, so the ion formation was much more efficient as compared to the without discharge or without filament. Then sample is ionized directly from the solution. It is protected from heat and many thermally labile analytes can be studied with little or no degradation. See, you first form there is a nebulization is there. You can see subsequently then there is the formation of the ions is there. Then there is the desolvation and then the formation of the species is there. As we saw here, the four steps. The four steps as we saw, first there is the formation of droplets. The charging takes desolvation. So the charging of the species forms is there before the desolvation. So that is why the analyte molecule is well protected with the help of solvent. And then after the desolvation, then the formation of the ions is there. So that is why it is protected from heat and many thermally labile analytes can be studied with little or no degradation. But I do not want degradation because I am interested in knowing the molecular structure of the species under interest, not the decomposed products. So that is why the decomposition I need to avoid and degradation have to be avoided. So thermospray is allowing this. The sensitivity is completely compound dependent, but generally very high sensitivity is achieved using the ionization techniques like thermospray with the filament and discharge. As I said, with the filament and discharge, the possibility of ionization increases a lot and you get a better efficiency of ionization. Naturally, the sensitivity also increases. Then presence of a buffer is usually needed, so must be present in the HPLC mobile phase. It helps in the basically the ionization. The decomposition of some thermal labile analytes occurs some of the not all. As I said, first I talk about advantages of this. That is, many of the thermal labile species are protected, but some of the very delicate species are still they may get decomposed. So there is a decomposition occurring. Then it is not a suitable technique for very high molecular weight. So if I have to study polymers, peptides, all the other biomolecules, then I can't do the thermospray because thermospray is not suitable for 1 million, 2 million, 3 million, this kind of molecular weights. It is suitable only for 1000 Dalton, that is 1000 molecular weight. So low molecular weight mass spectrometry, if I have got low molecular weight ions or the species, then I can study using the thermospray. But for higher molecular weight materials, like as I said, all biomolecules which are higher molecular weight compounds, they cannot be studied by the thermospray. Then the reproducibility of analyte results is affected by number of experimental parameters, so sometimes they are difficult to control. Then the formation of the adducts also may happen because some of the solvent molecules may form an adduct with the ions. So that may confuse the assignments. So these are some of the advantages. We saw the basic theory of thermospray. Then we saw the advantages of thermospray. We saw the disadvantages of the thermospray. So these are some of the other miscellaneous. Any questions on this, particularly the how it works? Thermospray?
No, sir.
So you are all clear? That is, this is the
Yes,
portion
sir.
whereby this is the LC portion. The liquid is coming, liquid which contains the solvent molecules, solid molecules also. It is coming entering here. There is a heated vaporizer is there, so it evaporates. Then there is a vaporizer thermocouple is there in order to control the temperature. Then there is a filament is there. Filament is here. So this filament basically charges the species and then subsequently This after the charging is done, then there is a desolvation of the species followed by the formation of the ions. So all those molecules which are the charged species of the ions, they get attracted to my lenses. Through these lenses, as I said, first negative, then positive, then again negative. My ions, they get extracted into the mass analyzer portion. All those molecules which are not charged, which are solvent molecules typically, they get pumped out because they are not attracted any places. They get pumped out from here with the help of pumping system. There is a repeller also put here, which is the positively charged repeller, in order to not allow the ions to wander here and there. Because if the ions come here, they will be lost and my sensitivity reduces. So that is why I am putting a repeller. So that repeller is pushing my ions positively charged species towards the mass analyzer portion. Where the solvent which is neutral charge, they all get pumped out. And then while pumping, there are nitrogen traps, liquid nitrogen traps are put so as to condense some of the solvent molecules to make efficient pumping or efficiently have the high vacuum in this. So it goes on pumping out continuously the excess solvents which are coming out, and then only the ions which are going from this system, they go to the mass analyzer. So mass analyzer contains only ions of my solute of interest and not the solvent. But still, as I said in the disadvantages, there is a possibility some of the solvent may form the adduct with my solute molecules, and then it may give me the molecular basically the ions, which may be confusing because the molecular weight may be entirely different because of solvent forming an adduct with my ion. So that higher molecular weight species will be seen. They may confuse me. Then many advantages are there. The first one is that it can take all kinds of liquid chromatography, that is normal conventional liquid chromatography, the 1 ml per minute, it can work, there is no problem. It doesn't need UPLC at all. Then the another major advantage is that it generally it avoids the thermal degradation, but only in a very sensitive species it still gives some degradation will be there. It has got a limitation of 1000 Dalton. It cannot operate more than 1000 Daltons. And if the molecular weights are higher like polymers and peptides, I will not be able to use thermospray. Okay. So with this, we have covered thermospray. Now the next is that we are going to see the APCI. Now, shall we take a break or we will continue with APCI?
Let's continue.
Continue or break? We take a break for 5 minutes. Again, it's 11:10. So
Yes, sir.
11:15, we will again continue. We will resume at
Okay,
11:15.
sir.
Okay.
Sir.
Okay.
Okay, sir.
So let us continue.
Yes, sir.
Can you see the slides?
Yes, sir.
Okay.
Yes,
The
sir.
next source which we are going to study, again it's a soft ionization technique and typically used only for LCMS. So what now we are going to study all the sources, that is ionization sources I am talking about, are all for LC. Now this is the atmospheric pressure chemical ionization source. So the name itself suggests. Now atmospheric pressure is the, so there is no high vacuum here, but you must remember that although the source may say atmospheric pressure, that the source there is atmospheric pressure, not in the mass analyzer. The mass analyzer portion has to be under high vacuum only, because if the ions which are formed are, they undergo any collision with other ions in the mass analyzer portion, then my ions will be lost. So the low vacuum or the atmospheric pressure is there in the only ionization portion, not in the mass analyzer portion. So the name itself suggests that there is a chemical ionization. Now when I say chemical ionization, in case of a liquid chromatography, HPLC, MS, when I am talking about LCMS, I have got large quantity of solvent is there, and I have got my solute of interest which is dissolved into that. Then it is injected into the my injection portion, that is my rheodine is there or maybe auto injector is there, and then subsequently passes through my column, and then under the pressure, under the basically the my solvent which is carrying forward continuously through the column, it separates all the my species into various peaks. Those peaks will come out from my outlet of my column, subsequently detected by the detector. Now so in this case, the large quantity of solvent is there always with my compound of interest. So the APCI takes advantage of that. So here, in case of a EI or CI, the chemical ionization happens because I am introducing an additional reagent gas. Okay. In this case, there is no reagent gas or any reagent liquid is introduced. The solvent itself works as a reagent liquid. Clear?
Yes, sir.
So now here, so that there is a lot of advantages of APCI, because let us first study how the APCI works, then we will see that what are the advantages and other things. Now it has got, again it's a atmospheric pressure chemical ionization is a spray technique. See, all these techniques are all spray techniques. So there is a spray followed by the ionization, then followed by taking care of those ions through the mass analyzer. So the difference in this only in these techniques is that, so thermospray and APCI are very similar. Only the difference is the method used for droplet generation and mechanism of subsequent ion formation. There is a difference in that. Okay. Let us see how APCI works. Can you see the diagram?
Yes,
Yes,
sir.
sir.
So this is a typical cross section of an atmospheric pressure chemical ionization. You can see here there is a HPLC inlet is there. Okay. Now there is a nebulizer or spray which basically generates the fine spray. Okay. The vaporizer inlet is there. So this is again heating up. So these are all coming. Now when these all droplets are coming out, okay, these all contain solute and solvent both. Okay. Now there is a corona discharge needle, or you can say it's a very high voltage has been put here. So I will show you another diagram in which it's more clear. So you can see here, this is the liquid chromatography portion is there. From a nebulizer is the gas liquid, there is a makeup gas is there is a gas plus vapor, this is the portion. Then there is a corona discharge needle which I showed here. This is the needle. Okay. Now this is the needle having a 6000 volts plus 6000 volt is the potential difference or the voltage which has been applied to this corona discharge needle. So this has got a very high voltage, 6000 volts. It's a very high voltage, 6 kV. Because of this, what happens is that these solvent molecules, they form ions. They will form ions. Now these ions will interact, these solvent molecules will interact with my compound of interest, and they will generate the ionic species from my compound of interest. So basically the solvent helps the formation of ions. So there is a water, there is M. Subsequently, these ions which are formed, they go from this exit. So you can see here also, these all coming out. There is a corona discharge which has got 6000 volt with the help of solvent molecules which are again ionized. There is a formation of ions from of my solute of interest. These all ions, they go into the this portion which is basically the mass analyzer portion, and there is a drying gas also. There is HPLC inlet here. This is a drying gas basically to take care of the solvent molecules, to remove some of the solvent molecules. It's more clear in this case. This portion you can see, this is 760 torr. This portion, this is which is basically the cursor where I am showing. It is the ion exit lanes. This is the ion exit cone, you can say. This portion is ion exit cone. This portion, which is whereby ionization is taking place, it is a 760 torr. 760 torr means atmospheric pressure, or 760 mm of mercury, which is typically the atmospheric pressure, 1 atmosphere, which is their normal hour pressure. So this is the portion which is a zero vacuum. There is no vacuum at all in this portion. This portion, once the ions are formed, there is a nitrogen continuously flowing through this. Okay, this nitrogen takes out some of these excess solvent molecules out, or these are called typically curtain gases. Only the solvent, ion molecules or the ions which are formed, they exit through this ion exit cone, because this portion is a high vacuum portion, which is 10 to the power minus 6 torr. Okay, this is 10 to the power minus 6 torr, and this is where the lenses, again the lenses are going to be, the first one is going to be negative, then subsequently there will be a series of lenses which will again positive, then again negative. So there is a collimation of the ions which are formed. So here once again we will just see there is a makeup gas or nebulizer gas liquid is there. So the liquid is coming from this, and I have got my gas plus vapor is there, that is my solid molecules are also there. This is the heated one, but here the charging of the species is not taking place. Then subsequently there is a corona discharge needle is there, which has got a very high voltage of 6000 volts. So this 6000 volts, they will now in this case the heat and gas flow dissolved the nebulizer droplets, yield a dry vapor of solvent and analyte molecules. Corona discharge ionizes the solvent first, which in turn acts as a CI reagent. So it is exactly equivalent to the methane or isobutane or ammonia which is used in case of a CI mode, chemical ionization, which is GCMS mode. In this case, the solvent molecules, since they form the ions, they will in turn as like a CI. Subsequently, this CI reagent which is formed interacts with my compound of interest. My ions are formed. These ions are formed through the corona, through this ion exit cone is there. Excess solvent which is all flown through the nitrogen. Nitrogen is continuously passing through this, because they are the species which are not going to be, they will basically solvent molecules, once they interact with my compound of interest, these solvent molecules get neutralized, they form normal neutral ions, they go from the system, or otherwise also they are not going to be very stable, whereas the molecules which are forming ions with the help of my solvent, they will go through this ion exit cone because of the various charges. The first one is going to be the exit lens, the first one lens is going to be negative in nature, which will accelerate my positive ion charge which are formed through this lens. Then subsequently there is going to be positive in order to collimate, and again there is going to be negative to accelerate. This portion is going to be mass analyzer portion, which is at a 10 to the minus 6 torr, whereas this portion which is ion formation is going to 760 torr. Is this principle of APCI clear?
Sir,
Yes.
uh, is that the dark line beside nitrogen gas? Is that the lens?
Yeah, it is a lens. It is basically, this is the ion exit cone. This is, see, what you have to do is that this is 6000 volt is there. Okay. Now your molecules of interest or the ions which are formed, it has got here also 600 volts is there, but a lower, much lower voltage is there. Okay, so somehow the repulsion also may take place, but subsequently here they are going to be negative in nature, so there is a continuously passage of the ions will be there. So this is the typical portion is called ion exit cone. So this portion I am exiting my ions, whereas this portion there will be condensables will be there. Some of the solvent condensables, the water molecule they will get condensed. They may go to the liquid traps. This portion nitrogen is carrying forward. Some of the solvent which is again excess solvent is coming is carrying forward continuously, which is going to the pumping system. Because of this lenses, this is going to be negative, this positive ions you can see MH plus is all attracted, they go here. This portion also is maintained at high vacuum, so the whatever the neutral molecules are there, they will again go out from the pumping system, whereas the MH plus, which is by ions of interest, it is not only one lens, this is only one lens, it is shown here, there will be series of lenses here, they will collimate by beam and might take it to the my mass analyzer portion. So this is basically ion exit cone. Clear?
Okay, sir.
Yes, sir.
You can see here also in this figure also, it is like the same thing. So there is a continuously the drying gas. Here it is shown like a vertical. You can see here. Here it is shown like this. So these are the drying gas typically. So this drying gas will take out the some of the solvent molecules along with the drying gas, and only the positively charged species they enter into this portion. And this portion is a mass analyzer portion. Okay.
Yes.
Now, what are the advantages? Advantages are many. So APCI or atmospheric pressure chemical ionization produces ions from the solution and compounds with a degree of thermal instability may be studied without their decomposition. Because what happens is that the solvent molecules is there, those solvent molecules are going to be charging, they will be forming the ions, subsequently they will form the my ions. So here I am not hitting too much to start with, I am just making them vapor, because thermal thing is not used for ionization. Unlike your thermospray, which basically I am using the either filament or I am using discharge electrode or basically the heated portion that is being used for the my just a minute, just a minute. Sorry. See, now I was telling you the advantages are many. As I said, the first of all, the solvent is making the ions. Solvent first getting ionized, then it is forming the ions. So the thermal phenomena are not there. It is basically the transfer of the charge from my solvent ions to my solute ions. Okay. So that is why in this case, although my compound is thermally unstable, it can be very well studied without much decomposition. Okay. It is very excellent techniques for the low and moderately high polarities. If it is a high polar material and low polar material also, I can study using APCI. It's again a softer technique because when this ionization takes place, it is through the solvent molecules. There is no much force. Unlike your electron ionization mode, whereby my 70 electron volts are bombarding my compound of interest, here it's a very soft ionization because there is a charge transfer only from my solvent molecules, which is positively charged species, to my solute, and it forms species which are positively charged but through a very soft technique. So it's a very softer technique. It can deal with a very high flow rates because unlike the your other techniques whereby solvent is a useless for as soon as the chromatography is over, for doing the chromatography or the separation of the compound of interest, I need solvent. But once the chromatography is over and my compound of interest along with the solvent is out of my column, my solvent has no role in other cases. Here the solvent has a big role because the solvent itself is going to be first getting charged, it is going to form positive ions, and subsequently it is going to interact with my compound of interest which is there in that, and it will form the ions of my compound of interest. So that is why as much as solvent is there, it will help for my ionization. But again, too much solvent also will load my vacuum system too much, so I will not be able to do that. But that is why you can see up to even 2 ml per minute flow rate, no problem at all. So you do not need to do APCI. You do not do. You do not require. I mean, essentiality is not there for a UPLC. Whereas other techniques like if I say, now when next time we are going to discuss about electrospray, in electrospray you will always need the UPLC because I am not interested in the higher flow rates because as much as higher flow rate will give me problems because solvent has no role in the electrospray, and as I said, once the chromatography is over, separation is over, that solvent has no role in thermospray also as well as electrospray also. Whereas in case of APCI, solvent has a big role, and that is why up to 2 ml per minute is all can be taken care of. So normally your columns which are 4.6 mm dia columns, they can be utilized easily. You don't need micro LC or anything. It is very tolerant to the presence of buffers in the mobile phase than ESI. So since solvent and other species are helping and it is solvent is in large quantities, this buffers are not much issue for, but still buffers used to be must be evaporable type. So unlike the sodium based or calcium based buffers, you will always prefer the ammonium based buffers. It is more tolerant to the changes in experimental condition than electrospray because solvent is anyway large quantities, the pool is there. So small variations in the solvent here and there doesn't matter much. So the gradient elution whereby I am ramping my solvent from one portion to the another portion. Like gradient, you are aware what is gradient elution? You are aware what is gradient elution? Anybody?
No, sir.
Gradient elution. In HPLC, you have got two systems typically. One is called isocratic and one is called gradient. What is isocratic? Isocratic is one whereby I start with a one mixture particularly. Say let us suppose as a simple case I say 40% methanol, 60% water is solvent system. From start to end, I will keep the same. 40% methanol, 60% water. The same thing in the beginning, 0 minute also. The same thing at the highest also. That is till my the run is over. That is called typically isocratic system. Okay. The gradient system is that the 40% and 60% is to start with. Maybe as a test case I am just telling it can be 30-70 also. But subsequently I am changing my ratios. That 40% of, let us suppose I am saying methanol, it may go to 80% or it may go to the 70% and subsequently water may increase or vice versa depending upon what is the gradient I want. So the solvent composition of my mobile phase continuously changes with time. That is called gradient elution. So you need two different pumps which are to be coupled. So there are again two types. One is low pressure gradient elution is there, and then there is a high pressure gradient elution. As I said, our topic, since it is not HPLC, I will not go into the details of that. But just wanted to tell you what is the term called gradient elution. Gradient means slowly changing the composition of that. Okay, so that is gradient elution. Now this gradient elution, if it is there, then ESI has got issues. Electrospray. ESI is electrospray ionization, which we are going to study in the next lecture. APCI is more tolerant to these changes. So there is no problem with APCI when it is a gradient elution. It has got some disadvantages also. APCI spectra can contain ions from adducts. Since large quantity of solvent is there and buffer also is there, it will always have adducts. See, if you tell solvent that you Baba you have to form positive charge, then transfer that positive charge to my compound of interest and get out. It doesn't happen like that. Solvent will play its role anyway. So solvent, the buffers, they will always have the adducts. They will form some association type of complexes with my compound of interest also. So then my molecular weight go up substantially. So then those peaks, they may give me some confusions in my interpretation of the spectra. Then structural information is not usually available because we'll see what is MSMS and cone voltage fragmentation afterwards when we go to the MSMS portion, MSMS topic. So MSMS is basically I will do the one more ionization, that is secondary ionization I will do, that is called MSMS. So this I am able to not do in this case, only purely APCI I won't be able to do that. So as I said, these are all softer techniques. Softer techniques means more formation of molecular ions, less formation of fragments. But in the case of a mass spectrum, I need both. I need always those fragments, I need the molecular ion both. So if I am able to give only the molecular ion and very, very less fragment, then also there is a difficulty. As in EI, there is more fragments, less molecular ion formation, then also there is a difficulty. So I want both molecular ion and fragments. So that is why here, since it's a softer technique, there is a less formation of fragments and so difficult to interpret. So I need to do MSMS in order to give more and more ions. APCI is not able to function effectively at very low flow rates. As I said last time, that since APCI more and more solvent is there, it will have more and more efficiency, because in the previous session as I said that I give you an example in that 22.4 liters is the gas formation, that is okay, but when the solvent is going to be working there and forming the ions, then I need higher flow rates really. I can't just have very small flow rates. If I go for a 25 microliter flow rate, then my solvent itself is a very small quantity. If my solvent itself is a small quantity, since ions are going to be formed because of my solvent of interest, so solvent which is used as a mobile phase, then my formation of the ion efficiency or the formation of ions also will be less, because ionization efficiency will be small. So that is why at very low flow rates APCI will not function very effectively. It is not a very suitable technique for which are charged in a solution itself, because I do not want solution charge. I want solvent has to charge my species or solvent has to form my ions. Are these things are clear?
Yes, sir.
Okay. So now we'll stop here. Any questions on this? See, as we saw in APCI, let us go to the back. I have got the HPLC inlet is there. Now here I am having the HPLC inlet, it is all solvent droplets are coming out. Now when the solvent droplets are coming out, the heat and gas flow dissolve the nebulizer droplets. There is a yield of dry vapor of solvent and analyte molecules in this case. There is a corona discharge. There is a 6000 volt in the corona discharge needle is there, which ionizes my solvent. So this ionizes the solvent, which is my solvent, and my M is there. There is a transfer of charge from my solvent, which is charged, to my M, formation of MH plus. There is MH plus formation is there. So this, in this case, solvent works as a reagent gas, just like a methane or isobutane or ammonia we saw. Here solvent works like a reagent gas. I do not have to introduce any in this case. So this one there form, some of this portion is a low vacuum portion, this portion is a high vacuum portion. So this solvent molecules which are excess in nature, they are taken out from this portion, as well as this is ion exit cone is there. Now this is 6000 volt is there, this 600 is there. So there will be some repulsion of some of the molecules, some of the ions, but there is at this exit there will be a negatively charged. So all those ions which will come to this portion, they will get attracted fast. Then there will be positive. Then again there will be negative. So these all with the help of this all ions which are formed positive ions, they will be taken to the mass analyzer portion. This is the high vacuum portion. The nitrogen continuously passes through this in order to flush out the excessive solvent and other molecules. So these all go out. Only the ions of my compound of interest. But you can't be selectively doing that, because ions always there will be some association type of buffers and solvent molecules also. So this MH plus will be there, plus there will be some additional ions which will be M plus my solvent will be there, or M plus my CH3CO minus, all those things also will be there. So there is a possibility that sometimes my mass spectra will be complicated. That is one of the major disadvantages of the APCI also. APCI has many advantages also. That is, first of all, we saw it forms directly from the solution. So that is the thermal unstable molecules can be easily studied. Then low to high polarities can be easily studied. It's a very soft ionization technique, and which usually enable the molecular analyte to be determined. So molecular ion is seen very easily. It can deal with a very high flow rate because solvent helps. So excessive solvent is not a problem, not very large quantity, but up to 2 ml there are no problems. Then it's very tolerant to the buffers generally, but sometimes it also forms the association type of complexes which are giving me problems. Then gradient deletions can be done easily using APCI, unlike the ESI. Then disadvantage, as I said, adduct is formation is there, that is the problem is there. Then more and more molecular ion formation or M plus H formation is there, but fragment is less because it's a softer technique. So I need to do MSMS or the cone voltage fragmentation frequently. Then it will not work at a very low flow rates because I need more and more solvent, or I will say some optimum quantity of solvent is needed in order to have the basically the APCI to function properly. And this is not suitable for the substance we are charged in the solution itself. So if they are already charged, because I do not want to have the charged species in the solvent, I want that my solvent molecules should first get charged, and it should interact with my compound of interest to form the charged species or the ions. So this is about the APCI and its advantages and disadvantages. Now one more spray technique is there, that is electrospray. Now we will stop here and we will continue next time with the electrospray. Any questions on what we have studied today? We have studied two techniques. One is thermospray and one is APCI. Now major differences between the your CI and EI is that CI EI are standalone ionization sources. You need an inlet system or you need an interface separately. So in case of GCMS, typically I told you transfer line is using an interface. You have got ion source separate, which is EI or CI, EI and CI or EI alone. That is the thing. Whereas here the interface is also used as a ionization source. So a thermospray was the first one which was used as an interface between the LC and MS, and APCI also is an interface between LC and MS. So this is not only an interface, it also ionizes. So it is interface come ionization source. This is how it works. So we have studied these two techniques. If there are any questions, I will be glad to answer. Otherwise, we will stop. Any questions?
No, sir.
See, overall, I want to ask one question. Am I going too speedily, or I have not seen, have you done recording last time also? Because see, what happens is that when you do a classroom, then you are able to see the faces of the students, whether something is being picked up or not, and more questions, some blackboard, all those things can be done. Now let us suppose when I say, let us suppose I have to tell you about the gas law, I can immediately draw that on the blackboard. But in case of this kind of present lectures, all those things are not possible. So that is why the feedback from your side is very essential. Have you recorded last time?
Sir, we recording the session, but we can't see the recordings in our team.
Why? But why don't you get it corrected?
Don't know, sir.
So it is
Sir,
some
it's
changes have been
because of the
in
update.
the app. Yeah. So for
Yes,
like
No,
sir.
no,
past
no.
1 month, we
But that
cannot
recording
access
is
any
where? That
record.
is in your server, college server.
Sir, it can be there.
No, but then you must ask because otherwise when you are recording, if you are not able to see that recording, then what is the purpose of that recording? Right?
Yes, sir.
So, can I get your feedback? How it is going? Now, this was the third lecture we did. How is it going? Good, bad, too speedily? You are not understanding anything. What is of your
Sir,
feedback?
it's good.
It's good, very good. I'm happy, but as I said, I must get your proper feedback. Why? Because see, classroom training or classroom lectures and this team lecture, there is a large difference. Okay, because I have to just ask questions only whether you understood or not, right? And many times I don't get a there is no reply also. So then anyway, one or two people will say yes, yes, yes. I have to assume and then I will go ahead like that. It is there. Where in the classroom, that's something is different. But this is a limitation because of Corona. We can't help really, right?
Yes, sir.
My request to you, all the people, is that you must revise. Because what happens is that since many of you are not from the chemistry background, this is hardcore chemistry. Let me tell you that. This is not organic reactions, but mass spectrometry is hardcore chemistry is there. Okay. So when it is
Yes,
hard, but
sir.
without mass spectrometry, you cannot be biologists. Okay, if you have to do bioanalytical chemistry, if you have to be experts, and you are, I know many of you people, either you will go for PhD or you will do, you definitely you will do job some good laboratories. Mainly the two objectives will be there, right?
Yes, sir.
So many of those who are doing PhD or even the laboratory work also, who want to do job in the pharma industry or any other laboratory, mass spectrometry is like a bread and butter every day. Without mass spectrometer or LCMS, you can't just work anything. Because biomolecules cannot be studied by GCMS. They have to be studied by LCMS. And so we'll be focusing a lot. We'll study definitely GCMS also. If something is like with a commercial lab, whereby agrochemicals or other small molecules are there, you can study them very well by GCMS. But otherwise LCMS, so many labs, I have seen the labs which are, they have got 10 LCMS, 15 LCMS like that. And LCMS is very costly machine, not less than 2 crores. Huh? Very, very costly machine. GCMS is that way cheaper. Still not cheaper means 75 lakhs. A good GCMS will cost you 75 lakhs. A good LCMS will cost you anything between 1.5 crore to 2 crores. That's the cost. It's a very costly machine. It is not like UV spectroscopy or infrared. They will be few lakhs. UV will be 3-4 lakhs or infrared will be maybe 8-9 lakhs. Whereas these machines are very costly. That is why the principles and the interpretation which we are going to see anyway, all going to be very, very important for you if you are to be successful bioanalytical scientist. So my sincere request to you is that you must revise. Okay?
Yes, sir.
Yes, sir.
Okay,
Okay.
sir. Yes, sir.
Then we stop here. All the best to you.
Thank you, sir.
Thank you.
So we'll
Thank you,
meet
sir.
on
Thank
next Saturday now. Okay? Bye.
Bye, sir.
you.